Now we can start classical mechanics. In that I'm studying J.C. Upadhyay's classical mechanics, now chapter 2, Lagrangian dynamics. So it begins with describing what is the use of these Lagrangian dynamics or Hamiltonian dynamics. Um, Earlier we studied Newtonian mechanics. Earlier we studied Newtonian mechanics. These Newtonian mechanics, to solve the Newtonian mechanics, any problem with the help of Newtonian mechanics, we need to find the forces, the vector equations. First we need to have an idea about all the forces, which all forces are acting in it. Which all reaction forces are acting in it. We need a picture of forces in our mind. Then we should draw vector diagrams, and we should resolve the components, vectors into these vectors into components, and then solve for unknowns. It's very difficult, long and messy, and time consuming also. So we don't need to know anything about these constraints, right? Like we should have an idea such constraints exist there. Constraints means I didn't talk about constraints. Constraints means, in simple terms, it is a restriction on the motion of a body. Suppose you consider a bead in a string. The bead is only bead can only move along that string, right? So the constraint decides how the body should move and how not to move. Okay, so then forces that enforce these constraints are called constraint forces. And so actually in our calculation we don't need to study deeply about these constraint forces, right? At this point, Lagrangian, when we consider Newtonian mechanics and the Lagrangian mechanics, or the analytical classical mechanics as in whole, we can say analytical mechanics is more powerful. Analytical mechanics consist of these Lagrangian dynamics, Hamiltonian dynamics, etc. Because Lagrangian we are studying Lagrangian dynamics, so we can talk about Lagrangian dynamics. In Lagrangian dynamics, we usually deal with we deal with generalized coordinates like position and velocity. So when we form the equations, automatically these constraint quantities, these constraints will vanish from the equations. So analytical mechanics is more powerful than Newtonian mechanics. It is not much messier. It's not messier. We can calculate the required quantities easily. Actually, constraints will not disappear. See, when constraints will disappear from the equations, that means constraint forces, we don't need to see in the equations. You will not find any constraint forces terms. Okay. See, now we are going to learn basic concepts regarding the motion of particles. So one of the fundamental concepts in the motion of a particle or a system of particles or a system is the position, right? So we need to learn, in motion means we need to learn how the particles or the system's position changes with respect to time. And so for that we need a coordinate system as a reference frame, right? We use this coordinate frame in mathematics and coordinate systems in mathematics and physics, so that we can analyze the system or analyze the motion of the system mathematically. There are different types of coordinate systems. So in 2 dimensions we have 2 coordinate systems, that is a Cartesian in 2 dimensions we have we can use the Cartesian coordinate system. Cartesian coordinate system. So here the coordinates are x and y. Okay, this is a rectangular coordinate system. Then it is normally used to describe the motion of a particle in a straight line or in a simple plane. Now then we can use plane polar coordinate system. Plane polar coordinate system. So in this the coordinates are the radius r and theta. Plane polar coordinate system is normally used in problems with circular symmetry. In circular motion or spiral motion, we can use plane polar coordinate system. See, this is the Cartesian coordinate system. Suppose this is a vector. This is x-axis and this is y-axis. So this point's position I can write it as x, y. But in plane polar coordinate system, this is x-axis and this is y-axis. Suppose this is the position of a particle. Its coordinates are written as r and theta, where r is the radial distance and theta is the angle measured from x-axis. This is theta. So here there is a particle. Now from this picture of this plane polar coordinate system, we can write r as square root of x square plus y square, okay, and theta as tan inverse of y by x. Next, in three dimensions, we mainly study the Cartesian coordinate system. Cartesian coordinate system. This is normally used in 3D systems. Here the coordinates are x, y, and z. Then the Cartesian coordinate system is normally used in simple systems, right? Then another type of coordinate system is spherical polar coordinate system. Here the coordinates are r, theta, and phi. Where r is the radial distance, theta is the polar angle, and phi is the azimuthal angle. I will draw a picture. This is the this is the x-axis. This is y-axis. This is our origin, and this is our z-axis. Now just imagine there is a vector. It stands like this. Okay, it's radial, and here there is a particle, and the distance from the origin to the particle is, or the radial distance is r. Now this angle is theta. Okay, this angle is phi. Now from this picture we can write r is equal to square root of x square plus y square plus z square. Right now, when you have to project to find the x and to find the angle phi and theta. First you need to project this vector r into the xy plane. Okay, this is the projection of r vector into the xy plane. Now this projection vector or this projection distance can be written as r sine theta. R sine theta. See, suppose this, consider this triangle. This is a right angled triangle, and here there is the angle theta. So r can be written as r. So this side can be written as r sine theta. Since this distance and this distance, the distance at the top, this one, and this distance, both are equal. So the projection distance is also r sine theta. Now we can calculate the x and y coordinates. X coordinate is equal to I forgot one thing. I made a mistake. This angle is phi. Okay, this angle is phi, not that full angle. The full angle is 90 degree. That is a stupid mistake. Now this is phi. So now we can write x as r sine theta cos phi and y as r sine theta sin phi. Okay, now we need to find now first we got the coordinate r. Now we have to find the coordinate phi. For that we can write y by x as, this r sine theta will get cancelled, so it will be sin phi by cos phi. Sin phi by cos phi, which is equal to tan phi. Right now Now tan phi is equal to y by x. So phi is equal to tan inverse of y by x, right? Then to find theta, see, we can observe that z coordinate is equal to r cos theta, right? Here this is the adjacent side. So the adjacent side is hypotenuse into cosine of that angle. This is r cos theta. So now from this we can write theta is equal to cos inverse of z by r. Now what is r? Cos, this can be written as cos inverse z by, what was r? R is square root of x square plus y square plus z square. So these are the transformation equations. See, z is equal to cos inverse, sorry. So these are the transformation equations. Theta is equal to cos inverse of z by square root of x square plus y square plus z square. Then phi is equal to tan inverse of y by x, and r is equal to square root of x square plus y square plus z square. These are the transformation equations in spherical polar coordinate system. Next we have the cylindrical polar coordinate system. Cylindrical polar coordinate system. Normally we use this coordinate system when in our problem we have axial symmetry. So here the coordinates are rho, phi and z. Okay. Now I will draw the picture. This is x-axis, z-axis and y-axis. Let here be the particle. Okay. Its projection onto the xy plane. This projection distance is called rho. Okay. Now phi is the angle from y-axis. This is phi to the projection distance. Then z is this distance, the particle's perpendicular distance from the x-axis. Okay, z or is a coordinate. Now we can derive the relation between the Cartesian coordinate system and the cylindrical polar coordinate system. Sorry, here I made a mistake. Actually, this is the x-axis and this is the y-axis. Similarly, here also this is the x-axis and this is the y-axis. Now from the figure we can write x is equal to rho cos phi and y is equal to, see this is the distance. So this distance x is equal to rho cos phi and this perpendicular distance is y is equal to rho sin phi. So y is equal to rho sin phi. Now y by x is equal to sin phi by cos phi. Rho gets cancelled. So we can write this as sin phi by cos phi is tan phi. So phi is equal to tan inverse of y by x. Now we got phi. Then z is same as the z in cylindrical polar coordinate system. I mean in the Cartesian coordinate system and cylindrical polar coordinate system. Cylindrical coordinate system, z is same. This is not polar coordinate. Cylindrical system. Cylindrical coordinate system. Then this rho can be written as, see this is a right angular triangle, right? This one. So this rho is actually square root of x square plus y square because it is the hypotenuse of this right angled triangle. So now we got three relations. That is, we found out the rho. Rho is equal to square root of x square plus y square. Z is same as the z coordinate of the Cartesian system. Then phi is equal to tan inverse of y by x. So these are the coordinate systems. Then now consider general coordinates q1, q2, q3. Okay. So generally in Cartesian this is a type of coordinate system. So here the coordinates are q1, q2 and q3. So the relationship between the Cartesian coordinate system and this coordinate system can be written like means the variables or the coordinates can be expressed as x is equal to x is a function of q1, q2, q3. Now if we include the time also, then we can write it as time as a fourth variable. Then here similarly we can write y is equal to, or y is a function as function of q1, q2, q3, comma t, and z is equal to a function, z as a function of q1, q2, q3 and t. So in general we can write the position vector. We always express the position vector as vector r, right? Position vector of a particle or a system as vector r. So vector r is a function of q1, q2, q3 and time t. So in fact these are the transformation equations from a general system to a Cartesian coordinate system. So here the q1, q2 and q3 are the generalized coordinates, or simply the a general system's coordinates.